Hi, we are Cecilia Telles and Maria Jose Chabuya Zamora, and we are going to present image formation. This is the outline of our presentation. And the objective is to analyze formation of images for two objects through a convex lens, and the specific goals are to obtain the focal length of each setup, determine the transfer magnification through two methods, and correctly classify each image obtained.
Okay, for the introduction, we have that a lens is a refractive device that produces different images depending on its characteristics. For these experiments, we used a convex lens, meaning that the light beam that passes through converges to one single point. To understand this better, we must first describe the focal point of a convex lens, which is the spot where all the beams converge. And the focal length is the distance from the optical center to the focal point, as we can see in the image shown below. It's also important to describe the distances of the object to the lens, which is SO, and the distance of the lens to the image will be SI. We also have the transverse distances, which is the height of the object, which is YO, and the height of the image, which is YE. When we work with thin lenses, it's possible to describe a relationship between the focal length and the distances of the object and the image. This relationship is known as the Gaussian formula, as we can see in equation 1.
We are also going to define transverse magnification, which is the ratio between the transverse distances of the object and the image, but we can also obtain this quantity using the object and the image distances as shown in equation 2. Also, we need to take into account the sign of the distances that we define to understand certain characteristics of the images and the object. For example, if an object is real or virtual, if an image is real or virtual, the type of lens we are using and the position of the object and the image, all of this is going to be given by the sign of the distances we define, and we can see these relationships with this table. Also, we can describe the image form in a certain arrangement in terms of class, position, orientation, and relative size. And this is going to depend on the object distance and the focal length and their values. And we are going to obtain the type if an image is real or virtual, the location, the orientation if it is inverted or if it is upright, and the relative size.
For the materials and equipment, for this experiment, we used a light source, a magnetic rail, a convergent lens, a graduated screen, and two images, which was an UTLAB shield and a train, or a locomotive. As we can see in the first image, or both images, which is the experimental setup, it is arranged on a rail in a straight line. In the first experiment, we used the UTLAB shield, the convex lens was fixed in a position, and the observation script was moved to obtain a clearer image. 7 measurements were made and photographs, and from these we obtained the transverse magnifications and its classification. In the second experiment, we used the same experimental arrangement, but with a locomotive. 4 measurements were made and photographs. With the data obtained, we calculated the transverse magnification and its classification, and on the last measurement, it was, instead of the locomotive, a lamp was used.
In the first activity, we determine the value of the object distance and the image distance. And applying the Gaussian lens formula, we could obtain the focal length. As we present in the first table, the error of the focal length was calculated using this equation. And then we estimated the average focal length and its uncertainty. And we compared the result with the one in the manufacturing manuals. We obtained an error of 1.02%. Now, for each measurement, we also determined the transverse magnification, but we used different methods that we observed in the equations. And we used first the definitions of transverse magnification using object and image heights, and also using the distances, object and image. And we obtained these two tables for both magnifications. Then we calculate the uncertainty associated with these equations. And finally, we compare both methods used by calculating the ratio between the values of the magnification, and then we calculate the complement of this ratio, which means we subtracted 1 from the value obtained. And we obtained these percentages. Finally, we describe the image obtained for each pair of measurements in terms of class, position, orientation, and size using the table we showed in the theory. We obtained that all the images were real, all were inverted, and most of them were augmented.
For the second experiment, where we used the locomotive image, to calculate the transverse magnification, we used two different methods. One using the relationship of the object and the image distances, as we can see in the first table, and the second one using the relationship between the object and the image heights, as we can see in the second table. As we can see, for the fourth measurement, it's not possible to obtain the image height because it is at infinity. It doesn't converge to a single spot. And to calculate its associated uncertainty, we use the equations as before, as we can see here, and we compared both methods by calculating the ratio between both values as in the first experiment, and these are the difference percentages we obtained. Then we classified each image based on its position, class, orientation, and relative size. As we can see, most of the images were real, inverted, and the relative size depended. From this table and the tables before, we were able to make the ray diagrams. For the first ray diagram, where the object distance is placed 2 times of the focal length, therefore we obtained a real image on the same size, but it is inverted. On the second ray diagram, the object is placed between the 2 times the focal length and the focal length, therefore we obtain a real, inverted, and augmented image. For the third ray diagram, where the object is placed in between infinity and 2 times the focal length, so we obtain an image that is real, it's diminished, and it is inverted. And for the fourth ray diagram, the object is placed exactly at the focal length. Therefore, the image goes to infinity and the rays don't converge on a single spot. Therefore, it's impossible to classify this image. Later, we answered the questions in the manufacturer's manual. Is it possible to obtain a measurement for M5, and how do we classify it? Yes, we rearranged the Gaussian formula for lenses and we cleared it for SI, as we can see in equation 6, and we obtained a value of 16.63 plus minus 0.5, and with this value we were also able to calculate the value of the transverse magnification, which gave us minus 2.3, and we classified both M5 and M6, as we can see, depending on its class, position, orientation, and relative size. With that table, we were able to construct the ray diagrams for both of them. As we can see in ray diagram 5, the object which was placed in front of the focal length, therefore we obtained a virtual image which is upright but augmented. And in the ray diagram 6, the object is placed seemingly at infinity, therefore the image converges to the focal point. However, it is highly diminished. It's only a point, but it is real and it is inverted.
Our observation. For the first activity, we observed that the measurements of the focal length obtained did not show a great variation, and therefore the average obtained was a good result. We believe that the imprecise measurements were the most likely sources of error. And we also noticed that in most cases, there was not a great variation between methods to obtain the transverse magnification. However, we believe that our measurements were poor when we tried to measure the height of the image format, and this led us to think that the transverse magnification obtained using the distances are better than the one using the heights. And for activity 2, there is an notorious variation between the methods used to obtain a transverse magnification, and we also believe that the height is not as accurate as the method using distances as in activity 1.
For the conclusions, in the first activity, we successfully determined the focal length of a convex lens by using the object and image distances, and we obtained experimental value of the focal length of 12.57 plus minus 0.2 with an error of only 1.02 in comparison with the literature. In both activities, we could measure the transfer of magnification for different combinations of object and image distances through different methods, and we compared them. We conclude that the method using distances gave a better result than the one using the heights. And in both experiments, we effectively describe the images formed for the different arrangement analyzed. And as we can see, these are the reference that we used. Thank you.